Hello, welcome. So I'm Michael Swanrick. I'm from a small company in Hanover, New Hampshire in the US called Creare, which in Latin is to create. We've been around for about 65 years. We have about 180 people. About half of those are engineers, and about half of the engineers are PhDs. Traditionally, we've been actually a thermofluids company, but we've branched out into a lot of different areas. For this talk here, we're going to talk about RASA 2.0 and Creare's part in that, developing an electrostatic precipitator. So a little bit of the history. P&L in 1992 started work on what we're calling RASA 1.0, which is the radionuclide aerosol sampler analyzer. The CTBT started their radionuclide network in 2000. And pretty much all those systems, or most of those systems, including RASA 1.0, use an impact or a HEPA-style filter to collect particulate matter for later analysis. There's a need to have faster collection, interval collection to match xenon gas systems that will require higher flow rates with lower power consumption. So what has Creare done? Creare has developed multiple ESPs, so electrostatic precipitators, and I'll go in a little bit about what that is, systems with significantly higher flow rates that still collect over 80% of small particles. We have shown we can do reduced collection times, lower power consumption, with the idea that you can collect multiple samples per day in a very flexible design. So, as I said, RASA 1.0 uses a HEPA-style filter, which is the schematic up in the upper left here. We're replacing that HEPA-style with an electrostatic precipitator. Electrostatic precipitator works by a high voltage on a small thin wire that creates a small corona around that wire that charges up creates some ions in the gas that transfers charge to particles that fly by. In a strong electric field, those particles get collected towards a grounded wall. In our case, our grounded wall is a very thin collection media that we then pull next to a detector. So what are some of the advantages? We can tune the collection efficiency by just changing the voltage. We can change the collection efficiency within 2 seconds. We can change from well over 90% down to 50%, for example. A very low pressure drop because it's basically an open channel. So most of the power consumption is done from the fans that pull air through. So if you have a very low pressure drop, you have low power draw. We collect on a thin material. This thin material can be wrapped up in different ways, placed in front of detectors, wrapped around detectors, lots of different configurations for a very flexible design. Some of the challenges with an ESP is it does require high voltage. So you need a high voltage power supply. You got to make sure your materials are compatible with high voltage and things like that. And because we're creating a corona, we do create a trace amount of ozone. So you have to, again, make sure all your systems are compatible with a trace amount of ozone generation. So we started this in 2018. This is originally funded by DOE and NSA. We're calling this Gen 0. This is really just a proof of principle system to show that an electrostatic precipitator can work. In 2002, we showed our first Gen 1 system. This is a full-scale system. It worked at slightly reduced flow rates, but we showed that this system is compatible with a future CTBT IMS type full-scale prototype. Just in the last few months, we demonstrated our Gen 2 system. We've improved the size of the system, the efficiency in the system, power has gone down, it's become more compact. So our system is quite flexible. Currently, we have an array of identical channels that can be expanded or reduced depending on flow rate requirements. And we can As I said before, we can change the voltage on either the corona wires, or we have a second stage of this, which is just an electric field. We can change that voltage. We can also have this as just a standalone manual system. So right now, you can collect on this media, and then you can pull that media forward as many times as you want during the day, and then that can be manually placed on a detector. As I mentioned, it collects on these flexible webs. We have a capacity for about 600 samples per spool, and I'll show you some of the spools. And that can be expanded actually up to over 800 if needed. So if you're doing a once a day type thing, you can have over 2 years worth of material without having to change webs. Just for scale, this is about 2.4 meters high in this picture here. As I said, high voltage can be a tricky thing if you're not doing it right. We simplified this. We have some series of high voltage bus bars that make the wiring quite simple. We have 3 wires coming out of the whole system to be able to operate. Here is a picture of the back side of it. These are all the webs. So if you have a whole bunch of channels, you need a web on each side of this channel. Our system has 16 channels, 32 webs. It's quite a bit of webs. And web handling became quite a problem and a challenge. We have worked through a lot of that. All of these webs are stacked on the back side of the system. They all go and turn and go through the air channels. That's where particulates come together, and when they come back, they all get combined. And this is for sample integrity, so the particles can't fall off. Everything gets combined into a package. So these are some recent results. One, we wanted to make sure we were always collecting over 80% of small particles. So these are 0.3 micron bin that we were tracking. And we've shown that we can run, this is an example data set, well over 80%. We've run for multiple hours. We've run, in lots of different conditions. So this is at 4 times the CTBT minimum of 500 meters cubed per hour. So this was running at 2,000. We could potentially run higher. We've shown that the system can work at even higher flow rates. We have live monitoring of the inlet and the outlet to show these collection efficiencies. We've run at quite high humidities. Actually, during our initial testing, wasn't planned, but Canadian wildfires brought very high particulate matter down to the northeast in the US. So we were 5 to 10x normal atmospheric conditions during some of this testing, which is good to see that it was working. We show our power draw is significantly lower than current RASA 1.0. If we were running at CTBT minimum flow rates with the ESP, we're running at 100 watts. So you can easily run that on backup power. If we're running at our full 2,000 meters cubed per hour with the electrostatic precipitator and the fans, we're at about 1 kilowatts. This does not include the detectors, so the cooling for the detectors and stuff like that. So if you wanted to package the samples up to present in front of a detector, how would that be done? This is in kind of prototype stage right now. You first need to advance the film, so this is at 10x speed. We're advancing the film through the system. We need a way to take up this extra material, and then we're going to twirl it into a package. So now it is twirling. And this is to make it into a compact form factor. And then the 2 acrylic plates that you see there, imagine those are detectors. It's going to slide in between 2 detectors. And this is to present in front of, if you wanted to run 2 detectors, you can run 1 detector. There's lots of different configurations But this nice tight sample package, I think that's it, enables the particles to stay well entrapped in there. Oh, there it goes. And then it can come back out. And then it unwinds. Sorry, the video doesn't seem to be working. There we go. So it comes back out. And then it untwists itself, and then the film advances. There's multiple ways to do this. We've explored different ways. This is in pretty early prototype stage. We worked with a whole bunch of different universities and capstone projects. This actually started during COVID when people were sitting there just coming up with crazy ideas. So. Can we go to the next slide? There we go, thank you. So what are we doing next? What are our next steps? We need to test in a bunch of different variety of weather conditions, demonstrate in more relevant environment. So just more seasons, more different humidities, different temperatures, just get a more robust data set. We currently have these prototypes in different sets. PNNL will talk about the detectors, but they're not currently, the ESP isn't combined with the sample packaging and the detectors. So that's coming up, and then fully automating all those together. So those are coming up. I just want to thank funding agencies. US Ch3 funded this work. PNNL has been very helpful in collaboration, and DRI. We do have a related poster, and Lance Liddy is not here, but PNNL also has a related poster. And then up next is going to be Harry Miley, who will talk about some of the detector work that PNNL has done. Okay. Thank you.
Thank you very much. All right, thank you very much. So, are there questions? And I bet that you have questions. So please use the microphones that we have here when you ask questions. Thank you.
Yes, thank you for this promising work. I've got a question about the collection efficiency. Do you have the same collection efficiency for all the aerosols?
Oh, no. So we were showing collection efficiencies for 0.3 microns. The minima for a ESP is similar to a HEPA filter, which is about 0.25 microns. So it actually goes up as you get to larger particles, and we do show that. I just didn't present that data. So the collection efficiency gets higher when you start going into 1 micron, 5 micron, 10 micron particles.
Okay, it's well calibrated, and you have the number per, depending on the size of the particles.
Yes, I mean, yes. So in our atmospheric aerosols, the number of 10 micron particles is very low. So we have quite a bit of data on 1 micron, but during the Canadian wildfires, we actually got plenty of 5 micron and even some 10 micron particles. So we do have some data on that.
Okay, thank you.
More questions?
Thank you. So another question on efficiency. How does this perform in different humidities? If you're really high humidity, I know you know the question is going to come, right? But we're very curious to see.
So yes, it does change. It does get affected by humidity. We have shown that we can still collect well over 90%. One thing that is that we're working on is making sure that we have consistent performance during high humidity, and there's not a chance of, because you're dealing with high voltage, of arcs or anything like that. So yes, it still performs well. It does have a slight reduced efficiencies, but we still can collect well over 80% at 2,000 meters cubed per hour. Is that?
Okay, I see no more, but I have one question also.
Sure.
So you mentioned that you have then high flow rate, and then the efficiency maybe goes down a little bit with flow rate.
Correct.
Yes. So is there like an optimum, like for that? And how high flow rate can you get? What's the limit of this technology?
So We wanted to make sure that we still checked the CTBT box of 80% collection efficiency for 0.2, 0.3 micron particles. If you didn't check that box and you just wanted to collect the most amount of particles, the actual optimal is higher flow rates. So we've run a similar system up to 3,000 meter cube per hour. What's the limits? It's hard to, the channel width, your pressure drop goes up quite a bit because your channel width and your wall effects get quite high. So for our system, there's a curve. It just gets to be challenging from a power perspective and a fan or blower and things like that.
Okay.
You would probably just make more channels rather than, so.
Okay, thank you. Right. Well, thank you again.
Thank you.
Thank you.